Now let's look at some examples in solving for probabilities involving sampling distributions of both the sample mean and the sample proportion. So for our first example, suppose that we will randomly select a sample of 64 measurements from a population having a mean equal to 20 and a standard deviation equal to 4. So in this particular example, we have the following given information. So a sample size of 64, a mean which is equal to 20, and a standard deviation that is equal to 4. Now we are asked the following questions. First, what is the shape of the sampling distribution of the sample mean? So in order to describe the shape of the sampling distribution of the sample mean, we first ask the distribution of the variable that is being described. So in this particular case, we don't know the distribution of the variable that we are looking at, but the sample size is 64. 64 is large enough, and therefore, according to the central limit theorem, the sampling distribution of the sample mean should be approximately normal. Okay. Next, find the mean and the standard deviation of the sampling distribution of the sample mean. So in other words, it's asking for mu sub x bar and sigma sub x bar. Now, according to the properties of sampling distributions, the mean of all possible sample means should be equal to the population mean. And since we know the population mean, which is 20, then the mean of the sampling distribution of the sample mean should also be equal to 20. Now, for the standard dev of the sampling distribution of the sample mean, that is expressed as sigma sub x bar. And to compute for this, we determine first if capital N over small letter n is at least 20. Because if the population is infinite, then the formula for sigma sub x bar would be the shorter one. But if the population is finite, then we will have to include the finite population correction factor. In this particular example, there is no information provided on capital letter N. So in most cases, when that is the situation, the capital N can be assumed to be a large value, and therefore dividing that by small letter n will give a number that is still at least 20. So in this case, we assume that capital N is a large number, and therefore we can use the shorter formula, which is simply sigma over the square root of n. So that should be 4 over the square root of 64, or 4 over 8, or a standard deviation of 0.5. Next, what is the probability that the sample mean is greater than 21? So again, it's no longer asking for the probability that x is equal to or greater than or less than a certain number, but it's asking for a probability involving a sample mean. So we express that as P of x bar greater than 21. Now, in the past, we have looked at several formulas in order to convert something to z. So the original formula for z is x minus mu over sigma. So x is the variable that is being converted to z, and to compute for the z-score of x, what we subtract from x is the average of all the values of x, and divide that by the standard dev of all the values of x. So here, we can't use this formula to convert x bar to z, because again, what we are converting is x bar and no longer x. And therefore, to convert x bar to z, we would need a slightly different formula. but the pattern of the formula is based on this formula that we have here. So if we are converting x bar, we follow the pattern of this particular formula to derive a formula for the z-score of x bar. So again, here, we subtract from x the average of all x. And therefore, here, to convert x bar to z, we will have to subtract the average of all sample means, which is expressed as mu sub x bar. Similarly, we divide this by the standard dev of all x bars, and that is expressed as sigma sub x bar. So this is now the formula that we will use in order to convert x bar to z. And these two parameters here were already computed in this previous step. So we will use these parameters in order to convert x bar to z. So in this particular question, we will convert x bar of 21 to z, and that should be 21 or x bar minus mu sub x bar of 20 divided by sigma sub x bar of 0.5. And when we compute for this particular z-score, we will get a z-score of 2.00. And searching for this probability, either using the standard normal table or using the normal distribution function in calculators, we should get 2.28% or 0.0228. So that's the probability that x bar is greater than 21. Now, how do we compute for the probability that the sample mean is less than 19.385? So we follow the similar approach. So again, note that we can convert x bar to z because according to the central limit theorem, the sampling distribution of the sample mean is approximately normal. And therefore, we can convert x bar to z. If the sampling distribution is not normal, then we cannot convert x bar to z. So this formula that we have derived earlier only applies to sample means that are normally distributed according to the central limit theorem. So again, going back, we convert 19.385 to z using the same formula. So that's 19.385 minus 20 over the standard dev of 0.5. And when we compute for this particular z-score, we will get negative 1.23. And computing for the probability or the area to the left of negative 1.23, again using either the standard normal table or using the normal distribution function of the calculator, we will get the probability of 10.94% or 0.1094. So that's the probability that the sample mean is less than 19.385. Now let's look at another example. So in this particular example, company advertises that any customer buying an air conditioner during the first 16 days of July will receive a 25% discount if the average high temperature for the 16-day period is more than 5 degrees above normal. If daily high temperature in July are normally distributed with a mean of 64 degrees and a standard deviation of 8 degrees, what is the probability that Aamco Heating and Cooling will have to give its customers 25% discount? So first, we are given the following information. So the random variable x pertains to the daily high temperature in July. And according to the problem, x is normally distributed with a mean equal to 84 degrees and a standard deviation equal to 8 degrees. Now the problem is asking for the probability that the company will give a discount. Now, in order to compute for this probability, we have to translate this first mathematically to determine what exactly is the probability that we need to solve for. So according to the first part of the problem, the company will only give the discount if the average temperature for the 16-day period is more than 5 degrees above normal. So it's not about an individual daily high temperature being more than 5 degrees above normal, but it's pertaining to the average of the first 16 days. So, in other words, this pertains to the probability involving a sample mean. And specifically, we want to know if the sample mean is more than 5 degrees above the normal. And according to the problem, the average is 84. So 5 degrees above this average is 89. So in other words, this probability pertains to the probability of getting a sample mean which is greater than 89 degrees. So this is the probability that we need to solve for. Now, in this particular example, in order to compute for this probability, we can try to compute for this by converting x bar to z, but only if x bars are normally distributed. So, according to the problem, x itself is normally distributed. That's why even if the sample size that we are looking at is only 16 and that is not large, since the variable itself is normally distributed, then the sampling distribution of the sample mean is already exactly normal. And therefore, x bars can be converted to z. Now, to solve for this probability, again, we just convert this first to z. And that should be 89 minus mu sub x bar, which is again equal to the mean of a population, which is equal to 84. Now for sigma sub x bar, again, this standard deviation of all sample means depends on capital N over small letter n. In this particular problem, we were given a sample size of 16. So the discount is based on a sample of 16. But do we have capital letter N? Do we have the population size? The problem did not explicitly provide the value for the population size, but X pertains to daily high temperature in July, and we know that there are 31 days in July. Therefore, capital N is equal to 31. Thus, if we compute for capital N over small letter n, that's 31 over 16, and that is clearly less than 20. Therefore, sigma sub x bar should use the formula with the finite population correction factor. So that should be sigma, or 8, over the square root of n, which is 16, multiplied to the finite population correction factor. So that's the square root of capital N minus small letter n over capital N minus 1. So solving for this particular z-score, we will get 3.54. And finding this probability, again, either using the standard normal table or using the normal distribution function of the calculator, we will get a very small probability of 0.0002. So based on this probability, what can we say about the promotion? According to our computation, the probability that they will give a discount is very, very low, which means that although yes, they are technically giving a promotion, a possibility of giving a discount, in reality, the actual likelihood that they will actually give a discount to any customer is very, very low. In other words, the discount seems to be quite misleading. The actual likelihood of giving out the discount is very, very low. Now let's have another example. Let's look at the supplier defects problem. So in this particular problem, a computer supply house receives a large shipment of floppy disks each week. Past experience has shown that the number of floss per disk can be described by the following probability distribution. So we have 0, 1, 2, and 3 as the possible number of floss per disk and their corresponding probabilities, 65, 20, 10, and 5% respectively. So again, X here pertains to the number of floss per disk, and the probability distribution is given. So again, we have the following values of X and their corresponding probabilities. So we have 0, 1, 2, and 3, and the probabilities are 0.65, 0.2, 0.1, and 0.05. So the first question is, calculate the mean and the standard deviation of the number of floss per floppy disk. So since we are given the probability distribution, we can use either the manual formula to compute for the mean and the standard dev given the probability distribution, or the faster way to do this would be to compute for the mean and the standard dev using the stat function in the calculator. So in this particular problem, we can input these four values of X under X, and then under the frequencies, we can put these probabilities. So the frequency for 0 is 0.65, for 1 that's 0.2, and so on. And then once the table is filled out, so again in the calculator, this will be the frequency column. So once all of these values are inputted, just use the mean and the standard dev functions to get the descriptive statistics. So for the mean, when we compute for this in the calculator, we will get 0.55, and for the standard dev, we will get 0.8646. So for this particular computation, we will round off to 4 decimal places. Now the next question is, suppose that we will randomly select a sample a sample of 100 floppy disks, compute for the mean and the standard deviation of the sampling distribution of the sample mean. Or in other words, look for mu sub x bar and sigma sub x bar. So again, we know that mu sub x bar, or the mean of all possible sample means, is always equal to the population mean. And since we know that the population mean is 0.55, then this must be the mean of the sampling distribution as well. Now for sigma sub x bar, to compute for this, again, we first determine if capital N over small letter n is at least 20. In this particular case, again, there is no information provided on the population size, but given the context, we can assume that the population is a very large number and it keeps on increasing, and therefore capital N over small letter n realistically can be assumed to be at least 20, and therefore sigma sub x bar is simply sigma over the square root of n. So solving for this, that's 0.8646 over the square root of 100, which will give us roughly 0.0865. So again, we can just round this off to 4 decimal places, or if you want, you can use the exact values until we get the final answer. Now for the third part of the problem, assume a random sample of 100 discs is drawn from each shipment from the supplier, with the shipment being rejected if the average number of flaws per disc for the 100 sample discs is greater than 0.75. What is the probability that the shipment for this week will be rejected and sent back to the supplier? So it's asking for the probability of an event wherein the shipment is rejected. And according to the problem, the shipment will be rejected if the average number of flaws per disc, or if X bar for the sample of 100 discs is greater than 0.75. So we express that mathematically as P of X bar greater than 0.75. Okay? Now again, before we convert this to Z, we ask ourselves first if X bar is indeed appropriate to be converted to Z, and that is only possible if X bars are normally distributed. So in this case, we don't know the distribution of the number of flaws per disc. X pertains to the number of flaws per disc, but we don't know if it's normally distributed. But the sample size is 100, that is considered to be large enough. And therefore, even if we don't know the distribution of the population, according to the central limit theorem, the sampling distribution should be approximately normal. And therefore, we can convert X bar to Z. So using the same formula we derived earlier to convert X bar to Z, this should be P of Z greater than 0.75 minus mu sub X bar, which we've computed earlier as 0.55, over sigma sub X bar, which is 0.0865. So computing for this Z-score, we will get 2.31, and from the standard normal table or the normal distribution function in the calculator, we will get the area to the right of 2.31, which is 0.0104 or 1.04%. So the probability that the shipment will be rejected is only 1.04%. So those are some examples of computing for probabilities involving sampling distributions of the sample mean. Now let's look at some examples for sampling distributions of the sample proportion. So let's look at this particular example. Suppose that we will randomly select a sample of 100 units from a population, and that we will compute for the sample proportion of these units that fall into a category of interest. If the population proportion equals 90% or 0.9, answer the following. So first, describe the shape of the sampling distribution of the sample proportion. So to describe the shape of the sampling distribution of the sample proportion, we look at the values of two equations. That's n times pi and n times 1 minus pi. So n is 100, pi is 0.9. So computing for these two equations, we will get 90 and 10, which are both at least 5. And therefore, the sampling distribution of the sample proportion is approximately normal. Next, find the mean and the standard deviation of the sampling distribution of the sample proportion. Or in other words, look for mu sub p hat the average of all possible sample proportions, and the standard dev of all possible sample proportions, which is expressed as sigma sub p hat. So according to the property of sampling distributions of the sample proportion, mu sub p hat, or the average of all possible sample proportions, is equal to the population proportion. And since we know the value of pi, which is 0.9, therefore the mean of the sampling distribution of the sample proportion should also be equal to 0.9. Next, to compute for sigma sub p hat, again, we also base it first on capital N over small letter n. If it's infinite, we will use the shorter formula. But if it's less than 20, we will have to include the finite population correction factor. In this case, capital N is unknown, and in most cases, again, when that is unknown, and also based on the context, capital N may be assumed to be a large number, and it would be safe to use the shorter version of the formula. So in this case, let's use that because we don't have a value for capital N. So the formula for sigma sub p hat is the square root of pi times 1 minus pi over small letter n. So computing for this, we will get 0.9 times 0.1 over 100, and we get the square root of that, and we will get 0.03. So the standard dev of all possible sample proportions is equal to 0.03. Now let's compute for the following probabilities. So first, find the probability that the p hat is greater than or equal to 0.96. Now we know that p hats are normally distributed. Therefore, to compute for probabilities involving p hats, we can convert this to z. However, we don't have a formula yet that converts p hat to z. But again, we can derive this formula using the pattern of the formulas when converting something to z. So if the value we are converting is p hat, what we subtract from p hat should be the average of all p hats. And that is written as mu sub p hat. And we divide that by the standard dev of all p hats. So this is now the formula that we will use in order to convert p hat to z. So we can also try to sketch this particular probability that we are solving for to guide us in determining the probability that we are solving for. So let's say this is the distribution of p hats. We know that the value at the center is 0.9, and we are solving for the probability that the p hat is greater than or equal to 0.96, which is greater than 0.9 or somewhere to the right of 0.9, and it's asking for the area to the right of 0.96. Therefore, we are solving for this particular area. And since p hats are approximately normal, we can solve for this probability by converting this to z. So that should be 0.96 minus mu sub p hat of 0.9 over sigma sub p hat of 0.03. So converting this to z, we will get a z-score of 2. And this probability is equal to 0.0228 or 2.28%. Next, solve for the probability that the p hat is between 0.855 and 0.945. So if we sketch this probability, again, the value at the center is 0.9. 0.855 is somewhere to the left of 0.9. 0.945 is somewhere to the right of 0.9. And we are looking for this area in between. So to compute for this probability, we will have to convert two values of p hat to z. So that's 0.855 minus 0.9 over 0.03, and then 0.945 minus 0.9 over 0.03. When we convert these two values of p hat to z, we will get positive and negative 1.5. So computing for this probability using the standard normal table or the normal distribution function in the calculator, again, we do this by computing for the bigger probability first and subtract the smaller probability. So that's the area to the left of 1.5 minus the area to the left of negative 1.5. We should get a probability of 0.8664 or 86.64%. Finally, if we were to solve for the probability that the p hat is less than or equal to 0.915, first, if we sketch this particular probability, again, we know that the value at the center is 0.9 and 0.915 is somewhere to the right of 0.9. Then the probability that we are being asked to solve for exceeds 1/2 of the overall sampling distribution. So we expect that the probability we should get later should be something that is more than 50%. So to compute for this probability, again, we convert this first to z. So that's 0.915 minus 0.9 over 0.03. Converting this to z will give us a z-score of positive 0.5. And therefore, the area to the left of 0.5, according to the standard normal table or the calculator, is 69.15%. So the probability of p hat less than or equal to 0.915 is 69.15%. So those are some examples of how to compute for probabilities involving sampling distributions of the sample proportion.